This is section 2.6, related rates. Now we've seen how the chain rule can be used when we find dy dx implicitly. Another important use of the chain rule is to find the rates of change of two or more related variables that are changing with respect to time. So these derivatives will be with respect to time. For example, if we have the volume of water in a tank and we're draining that tank or we're filling that tank, either one, the rate at which the volume is changing with respect to time, in other words, the flow rate of the water, will be the derivative of volume with respect to time. And that would represent the rate at which volume changes. With respect to time. Now, with the ones like this that involve time, I'm going to ask that you limit yourself to Leibniz notation, because if there's an equation and it has other variables, like let's just say that the volume equation is, I don't know, 1/3 pi r squared h, which is the volume of a cone. Like if we had an ice cream cone and it's got ice cream in it, of course, and it's below the top and you develop a leak, and your ice cream is dripping out at a certain rate, what would the rate be? Well, let me draw a bigger cone. This is what we consider the radius of the base of the cone. And I've got the inverted cone drawn because that's the way usually it would be held if it were an ice cream cone, so that makes sense, I hope. And then if you go from the center of that circle, that's the base of the cone, and draw a line from the tip of the cone to there, that's a measure of the height. And of course, those are at right angles. The radius and height are at right angles. Okay, so anyway, I was saying use dv dt if that's what we're doing, because if you wrote v prime, the question could be, do you mean by that the rate at which the volume is changing as the radius is changing? Because that's actually a thing, because when the level of the ice cream is down to here, the r there is smaller. And so the rate at which the volume is changing when you're way down there with respect to r is going to be different from when it's a full cone. Or perhaps you have a dv dh, which, similar to what we just talked about, that's the rate at which the volume is changing with respect to the height of the cone. Or we could be talking about, which is what we want to be talking about, the rate at which the volume is changing as time goes on, over time, or with respect to time. So v prime is ambiguous, and I really don't know which of these you mean when you write v prime. So because of that, I really want to stress that you should be using Leibniz notation for the related rate problems. Okay, so there's another problem with the equation I just wrote, and that one was chosen on purpose. We actually have three variables in that problem: the volume, the radius, and the height. And so when we take a derivative with respect to time, we've got to be aware that all of those are going to be changing at a certain rate with respect to time. So the rate at which the radius is changing will be called dr dt, and the rate at which the height is changing will be called dh dt. And of course, the rate at which the volume is changing is the dv dt that we talked about earlier. So I really want us to do this one. That's the one we're going to be finding, because this is a rate with respect to time. So if we take that equation that relates these variables to each other, and I will tell you sometimes the equation that relates the various variables to each other will be given like this, and I would not expect that you memorize the volume of a cone. I mean, if you happen to know it, that's great, but I'm not going to ask you on purpose to go ahead and extra add this to your list of things. Volume of a cone is not one of those I want you to memorize. But there are certain things that I do expect that you would know, like, let's start with distance formula for lengths. We could ask for area, perimeter of rectangles, squares, circles, and there are perimeters called circumference. Area, perimeter of a triangle, volume of a cylinder. That's one I expect you to know. So let me write that one down so that that's something that you realize, yep, I'm supposed to know that. If this is the radius and this is the height perpendicular to that, then the volume of a cylinder is pi r squared h, and the volume of a rectangular prism, also known as a box, if this is length and this is width and this is height, the volume of that rectangular prism is length times width times height. Okay, so those are the basic formulas from geometry that I'd expect you to know. If it were volume of a sphere or surface area of a sphere or surface area of rectangular prism, something like that, I would give you that formula in the problem. But if it's one of those simpler figures, I would expect that you have those memorized and could use them as needed. Okay, so anyway, back to the cone. If we use implicit differentiation, because we're trying to find dv dt, the rate at which the water flows, let's say the ice cream flows out of this thing, we're going to take the derivative on both sides with respect to time. So notice none of these variables are t, and so all of them are going to be thought of as functions of t that will change as time goes on. I'm going to write that 1/3 pi as pi over 3 because I can. Okay, and so when we differentiate with respect to time, the derivative of volume with respect to time is dv dt. On the right-hand side, that's a product, and I, again, am going to think of the constant times r squared as the first function. I'll think of h as the second function. So using the product rule, that's going to be first function times the derivative of the second one, and the derivative of h with respect to t is dh dt, plus now the second function times the derivative of the first. The derivative of a constant times something is that constant, times the derivative of that something. The derivative of something squared is 2 times that something to the first, times the derivative of that inside something, which is r, with respect to t. Okay? And so this formula, we could factor out the pi over 3 if we wanted to, and I guess I will. dv dt would depend on what the size of the radius is, the rate at which the height is changing. I'm just listing all the things that I'm writing down as, what they mean idea-wise, and what the height is at any particular point in time, what that radius is again, and the rate at which the radius is changing. So the rate at which volume is changing depends on a lot of things. The rates at which both height and radius are changing, and the specific height and radius values at any particular time. Okay, so that's good. All right, now let's do another example. This is now example 1. The variables x and y are both differentiable functions of t and are related by the equation y equals x squared plus 3. Find dy dt when x is 1. Find dy dt when x is 1. Given that dx dt, the rate at which x is changing with respect to time, is 2 when x is equal to 1. Okay, so for these related rate problems, the first thing you're going to have is an equation that relates the variables that are changing with respect to time. Since dy dt and dx dt are both given as part of the problem, I need to have an equation that relates the y and the x to each other. This time it happened to be given, but other times they may have some kind of relationship that you're going to have to figure out that equation yourself. So this time it's given, so you need that equation. Once you have that equation, you're going to differentiate on both sides with respect to time, with respect to t. Some are simpler than others. This one is pretty simple looking. So this is kind of getting you through the basic ideas with an easy one. So the derivative of y with respect to time is simply dy dt. And the derivative of something squared is 2 times that something to the first times the derivative of that something with respect to t, plus the derivative of the constant 3 is 0. So plus 0, I'm not going to write that. Okay, now they ask us to find dy dt, so find dy dt, and it's already by itself, so I don't have to solve for it. When x is 1, so this is the symbol that says I'm evaluating dy dt when x is 1, and so I'm going to substitute into the formula I have for dy dt, where every x is a 1, and when x is 1, I'm going to use that other piece of information that said dx dt is known to be 2, so I can substitute in 2 when x is 1. And so the answer here is 4. Okay. So the basic steps are going to be, you need an equation that relates your variables. You'll be given some of the rates and values in the problem, and you're going to have to differentiate, use implicit differentiation, differentiate with respect to t on both sides, and then start substituting in the things you know or can calculate and find the answer to the question that was posed. So let's look at example 2. Go ahead and read that, example 2, to yourself. All right, so we've got a pebble dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. Okay, as soon as I read that, when they give me a rate, at which something's changing, I'm going to write an expression for the rate at which that thing is changing. dr dt is the rate at which the radius is changing, and it's at a constant rate of 1 foot per second. Now, since it's a rate, you need to realize that rates can be positive or negative, because it could imply growth when the rate is positive, or shrinking or decreasing if your rate is negative. And so you need to read the words of the problem, and it says increasing. That implies that it will be a positive 1, and foot per second is the units. And as soon as I see units, that means that my answer better have units. So it's just kind of a heads up. And what I'm doing is I'm translating the question, all the information from the question, into symbols. And that really does give you a lot of information. So you might make a habit of doing that. When the radius is 4 feet, when the radius is 4 feet, at what rate is the total area A of the disturbed water changing? So in other words, they want us to find what? The rate of the area. Okay, so that would be dA dt. Okay, so that's what it says. So since they told us it was a circle, and the things that I have mentioned as things that are changing are the radius and the area, and that it's a circle, I need to come up with my own equation that relates area and radius to an equation that has those two variables in it for a circle. And of course you should know, this is one of those that I would say you better know this one. The area of a circle is pi r squared. So we this time had to come up with our own equation. They didn't give it to us. Then once we have that equation, use implicit differentiation and find the derivative on both sides with respect to time t. Okay. Well, the derivative of a with respect to t is simply dA dt. And the derivative of a constant times something is that constant times the derivative of something. So the derivative of r squared is 2 times r to the first times the derivative of the inside something, dr dt. Okay, so we're supposed to find dA dt. So when are we supposed to do that? We're supposed to find dA dt when r is 4. So that's going to be pi times 2 times 4 times, do we know dr dt? Oh yeah, that was one of our first givens. dr dt is 1. And so we end up with 8 pi. Now what are the units? I'm going to tell you that Leibniz notation, this dA dt, is super good for units, because if you look at the units of the individual items, the numerator units, dA, area is going to be measured when lengths are measured in feet. Area is going to be square feet. And then the denominator of dA dt has the variable t, and t, because this was given as in feet per second, is going to be, time will be measured in seconds. And those are the units for this answer. That's square feet per second. That's the rate at which the area is changing when r is 4 feet. Okay. So let's go to the guidelines that they give us. And this is basically what I've been saying, so I'm not going to necessarily read that. I do want to say, though, that a lot of times drawing a sketch of what's going on might help you. I didn't draw a sketch of a circle because I figured you could imagine that without my drawing it. But had I done so, here's one of the circles, and there's the radius, and then from that we would have said, oh, the area formula for that is a equals pi r squared. But I didn't draw the picture that time because I didn't think you really needed it. But many times a picture can really, really help. But otherwise, the steps are, pretty cleanly what we just did. Then in the next slide, there are different examples. And we did this earlier. Translating from words to symbols is really important. So like if you see the velocity of a car after traveling for 1 hour, so that's when t is 1, is 50 miles per hour. Velocity of the car, if x is measuring your distance, that means that dx dt, the rate at which the car is traveling, is 50, and the units are miles per hour. You can read all of these yourself, so read them carefully. Water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. If V is the volume, then they just gave us the rate at which that volume is changing, which is dV dt. So please read all of those and make sure that you understand how the expression is come up with. Now, notice that we created, the problem itself didn't have this. In the right-hand side, that mathematical model, we had to create a variable for each of the things that's involved. So we had to create for the first one, x is the distance traveled by that car. V was the volume of the water. T, of course, is time. The angle of revolution, we had to call that something, so we might call it theta. The number in the population of bacteria, we might just call that x. Of course, that doesn't mean you have to use those particular variables, but for words like volume, I'd use V. For area, I would use A. Something that's, everybody would know what you mean. Okay, so let's look at example 3. A ladder is 15 feet long, and it's leaning against a building so that its foot is on level ground and the top is on the wall. Okay, let's see if I can draw this. One thing about mathematics is when they set up a problem like this, they always assume that the ground is level, even if they don't mean it, and that all buildings are perfectly, not that they don't mean it, that they don't state it. They're going to imply that the ground is always flat, horizontal, which of course is not true, but we're going to make that assumption on every word problem. And every building is vertical, unless it's a problem specifically about the Leaning Tower of Pisa, then assume that it's vertical, because we need that right angle to help us with this problem. That's important. Okay, so we have a ladder leaning against that wall. Here's my ladder. And I'm going to label the picture with the very first piece of information they gave me. The ladder is 15 feet long. That's not a variable. The length of the ladder is not changing, okay? That's a constant value, 15. Okay, the foot is moved away from the building. So one of the things I like to do is when I'm measuring distances, if I've drawn a picture, if the foot moving away from the bottom of the wall, if that's a horizontal measure, I'm going to generally call that x on purpose. So I'm going to decide that I'm going to call the bottom of that triangle x. That's the distance between the base of the ladder and the bottom of the building at the ground. Okay, and I'm going to call that x. And when they tell me that the foot is moved away from the building at the constant rate of 1/2 foot per second, that means I now have something to call my my derivative. The rate at which x is changing with respect to time is 1/2. Now, is it positive or negative? And you need to be very careful about this. Is x growing or is x shrinking? If it's moving away from the wall, x is growing. If it's being pushed toward the wall, x is decreasing. So if it were being pushed toward the wall, I would need a negative dx dt, because x getting smaller would mean that dx dt is negative. But if the bottom of the ladder is moving out from the wall, x is growing, which is the case in this problem. So it's positive 1/2. And I'm going to go ahead and write the units in my information. That way I have them recorded so that when I write my answer, I know what the units should be. Okay, that's what we're given. So let's read the first question. A. Find the rate at which the ladder is moving down the wall. Okay, so find what? Well, the rate at which the ladder is moving down the wall, we're going to have to measure that distance from the bottom of the the floor, the ground level, to the top of the ladder. And again, generally speaking, if I have my druthers, I would call any vertical distance I'm measuring y. Horizontal distances I'll call x. And if a distance happens to be neither horizontal nor vertical, I tend to call that y. I tend to call that z, excuse me. I tend to call things that are neither horizontal nor vertical, I tend to call them z. All right, so anyway, we're supposed to find the rate at which the ladder is moving down the wall, so find dy dt, the rate at which y is changing. And if it's down the wall, what kind of number do you expect dy dt to be? Is y increasing or decreasing? And that should inform you about what kind of answer you're expecting. And we'll come back to that and make sure that our expectations are met. I'm not telling you what I think it should be because I want you to think about it while we're working the problem. Okay, find that rate when the foot is 9 feet from the building. So find dy dt when the foot is 9 feet from the building. So that's when what is 9? Yes, x, when x is 9 feet. Okay, so to get started, we have to come up with an equation that relates x and y, because those are the differentials we have, dx and dy, an equation that relates x and y to each other for this problem. Now, since I drew a picture, it's probably obvious that we have a right triangle and that leg squared plus leg squared is equal to hypotenuse squared. And notice that is a constant, so that's 15 squared, not a variable thing at all. So now that we have the equation that relates the variables to each other, now do implicit differentiation with respect to t on both sides to get the related rates. So the derivative of something squared is 2 times that something to the first times the derivative of that something with respect to t. So the next one looks very much the same, 2y dy dt. And of course the derivative of a constant is 0. All right, so now I would start well, I guess we can solve for dy dt if you want to. Let me do this twice. I want to do it once where we solve for dy dt first. I'll do that over here to the right. So to solve for dy dt, I would subtract 2x dx dt from both sides. And then to solve for dy dt, divide both sides by 2, so the 2's will disappear, and y. So I divided both sides by 2y. And then we can find dy dt, which is what we're asked to find, when x is 9 feet. So that'll be the opposite of 9 times, divided by 9 divided by y. Now, this is going to happen quite a bit, that one of the values that you need to have, like here we need to know what y is when x is 9, is not given. And you're going to have to calculate it yourself. And so this primary equation we came up with that related x and y to each other is going to be useful for that. Because if x is 9, that means that when that's true, x squared, which would be 9 squared, plus unknown y squared will be 15 squared. And so y squared is equal to 225 minus 81. 225 minus 81 is 144. And so that means y is 12. Right. So that's going to be 12. Calculated, not given. And calculated using the equation we came up with. Okay. Anyway, so I substituted in for y, and then dx dt was given. It was positive 1/2. And so our answer is going to be negative 3/8. Okay, so now let's interpret the answer in terms of the question. Find the rate at which the ladder is moving down the wall. So the ladder, and I would expect that if the question is in words, maybe your answer should be as well, which I didn't do earlier, but pretend like I did because I forgot to do it. Sorry about that. The ladder is moving down the wall. And what's the rate? It's actually positive 3/8. And where did the negative go? That negative is expressed with the word down. So rates at which you're moving, like going from Dallas to Fort Worth or Fort Worth to Dallas at 50 miles an hour, we're not going to say going one way is positive and the other way is negative. The speed at which we're moving is what is important, and the word down tells us which way. And so that picks up the negative. And dy dt, since y is measured in feet as well, and divided by t dt, so t is in seconds, so that's going to be 3/8 foot per second. Okay, so anytime you express a rate, you're going to need a word that indicates the direction, and the number should be positive, the rate. We're going to take the absolute value, basically, of that answer and use the positive or negative sign to be expressed using words. Okay, part B. Find the rate of change of the area of the triangle made by the ladder, the floor, and the wall. Okay, so we want to find the rate at which the area is changing, so find dA dt. Find dA dt. Oh, I forgot to do the other one the other way. Darn it. Okay. Since I just remembered, let me just erase everything I just wrote. Back up. Okay. So the other way you could have done this is without solving for dy dt, which is what we're going to end up with. Start substituting in with everything you know. So x is 9. dx dt is 1/2. Y is, oops, forgot to write plus. Y is unknown until you realize, as we did above, that we have to solve for y, because the only thing that can be unknown is the thing we're solving for. So we'd have to figure out what y is, and of course y was 12, that earlier calculation, times dy dt, the thing we're solving for, which is dy dt when x is 9. So just substitute directly into the equation that you get after you've done your implicit differentiation, and then solve for your unknown. So this is going to be 9 plus 24 times dy dt, evaluated when x is 9, equals 0. So to solve for dy dt when x is 9, I would first subtract 9, then divide by 24, and simplify. And of course I get the same answer, obviously. So it's kind of up to you which of those two ways you do that. I don't really care. They're both valid. And don't forget that dy dt equals -3/8 is not enough. I then want you to interpret it using words. So the negative comes out as a down the wall, and the 3/8 is the rate at which it's changing. Okay, so I started to write the other one and got sidetracked. So we're supposed to find dA dt. When the foot of the ladder is 9 feet from the building. So again, when x is 9 feet. Okay, see if you can set this one up and solve it yourself. Okay, let's see how you did. First, you have to come up with an equation for the area of that triangle. So let's look back at our picture. Since it's a right triangle, the best thing to do for the area is to realize that one leg is the base of the triangle, the other leg is the height of the triangle. For right triangles, it's really easy. In our case, that's going to be x and y are the base and height. And of course, the area of a triangle is 1/2 base times height. So the area, in terms of our variables, is 1/2 base times height. One thing I want to make sure you are very careful about here is that this is not the time to start substituting. This equation is true no matter what x is, and we have to find the rates, the related rates, at any point in time, not just when x is 9, before we can put in x is 9. So please be aware that we cannot substitute yet. Like this equation up here, x squared plus y squared equals 15 squared, we didn't substitute then. We found the derivative implicitly with respect to time first, and then we can go about substituting. Okay, so differentiating with respect to time on both sides. And on the right side, again, I'm going to treat the 1/2 x as my first function when I'm doing that product rule. Okay, the derivative of a with respect to time is simply dA dt. And on the right, we have a product, so it's going to be first function times the derivative of the second one with respect to time, plus the second one times the derivative of the first. And the derivative of 1/2 of x is 1/2 times the derivative of that variable, dx dt. Okay, so I think I'm going to just substitute in. I'm not going to, well, it is solved for dA dt. What am I saying? That's not really much of a choice. It's already by itself, so that's good. Find dA dt when x is 9. So now we substitute in everything we know. X is 9. dy dt. Do we know what dy dt is when x is 9? Yeah, that's from part A. So a lot of times part B uses information from part A. So you'll need to make sure you get this right. And what is dy dt? Yeah, you better put in the negative. dy dt was -3/8. When we interpreted what that meant, we didn't say the negative, but dy dt is negative, which implies that it's shrinking. The value of y is getting smaller. And do we know what y is when x is 9? Yep, we found that earlier as well. That was 12. So a lot of times you're going to rely on stuff you already know. And do we know dx dt when x is 9? We do, don't we? Wasn't that given? Let's go back up here and see. What was dx dt? Way up here at the beginning. It was given, there in green, 1/2 foot per second. So dx dt was 1/2. So we didn't have to calculate anything extra this time because we'd already done that in part A. Okay, so do this arithmetic, and you should get 21/16. And what are the units? Now the area, since lengths are measured in feet, the area would be square feet per, and the unit of time is still seconds, right? Okay, so let's interpret the answer that we just found in words. The area of the triangle is doing what? Growing or shrinking? Increasing or decreasing? Well, since it's a positive answer, that means it's got to be increasing. At a rate of 21/16 square feet per second when x is 9 feet. And there's your answer. Okay, so that ends this section. Ask me in class to present more examples to you if you need them. I have a bunch of them, and I can certainly do that with you so that you get the idea of how to set these up. I think it's well worth our time doing some more examples, but I'd like for you to ask me about that in class, and I'll come with plenty of examples to work together. Okay, that ends this lesson. I will see you in class.